is going to depend on the size distribution. And then I'm going to assume that I'm going to assume some ejection efficiency, that in this case I'm going to take it from some simulations of how effective these stellar encounters are at ejecting this material. So, so I can plug that in, and then I can do the same for the contribution of post-main sequence mass loss to the release of these exo or clouds. And in this case, again, it's going to depend on the initial mass function, how many stars, the number density of stars per stellar mass, how many stars are in the have left the main sequence, they are already in the post-main sequence phase, how many objects I have per stars for objects that are larger than Oumuamua. And in this case, what is the efficiency of post-main sequence mass loss is going to depend on the stellar mass. Stars that have a lower mass, like the sun, they are not as efficient because they don't lose as much mass. But stars, sorry, stars that have higher mass, they are more efficient. They lose more mass, so when they lose that mass, they release more objects. The percentage of objects from their XOR clouds that get released is higher, right? So I plug these numbers in here, and then I compare them to the number of objects that we infer from the detection of Oumuamua. And again, when you compare all those numbers, the number of objects, the number density of objects larger than Oumuamua that we infer from its detection is 2 times 10 to the 15 objects per cubic parsec. And this compares to these numbers here. What I expect from stellar encounters, the number of exo or cloud objects that I expect to release from stellar encounters is about 10 to the 12. For this range of stellar masses, for lower mass stars, about 10 to the 13th. So you see that lower mass stars have a larger contribution. And then from post-main sequence mass loss is about 10 to the 13th. So, as before, I cannot account for as many objects as I infer to exist based on the detection of Oumuamua. So again, we don't know where this thing is coming from, and we just cannot account for that much mass, assuming again that this object is representative of an isotropic distribution. And I think that's the key. I think that that Oumuamua might have originated from a nearby system that is not representative of an isotropic distribution, and that and this is why we cannot account for as much material as we infer based on its presence. So I think this object might have been ejected from a nearby system, and that the ejection might not be isotropically distributed. And I think this agrees with the fact that the color is not as red as you might expect from objects that have been exposed for a long time to, like in the outer solar system, for example, right? That's been exposed to space weathering from cosmic rays, from ice and plasma. And also, Oumuamua is tumbling, so it's rotating in a way that with time, because of the tides, it should have died down, and it should have the tumbling would have died down like within a giga-year, right? And it's still tumbling, so probably has not been traveling for that long. And and then the kinematics also seem to indicate that because it's moving very close to the local standard of rest, within 3 to 10 kilometers per second, within the local standard of rest, this might mean that it had not had time to be dynamically heated. So, so maybe this indicates that Oumuamua wasn't released that long ago, and this might be what you would expect if it was ejected from a nearby system. And if it is ejected from a nearby system, then it doesn't make sense to assume that it's representative of an isotropic distribution, and this is why we cannot account for that much mass. But this is just speculation. Obviously, we cannot prove any of this, but for sure, we don't know what the origin is, and we have a problem accounting for as much mass as it implies. Yes?
Is this conclusion helps to explain the fact that it didn't have a tail, or does it make it even harder?
That I'm going to talk about that at lunch. So I don't think this. I mean,
because this, I think the first one about the weather and the cosmic ray was invoked. I mean, this has an effect on the composition of the Oumuamua, and then on the conclusion if it should have a tail or should not.
Yeah, but as you know, there is no agreement on that. But yes, there could be a space, but you could still have I mean, you could have a crust that is that has no volatiles, right? But you could still have volatiles underneath. So I think you could have a space to see some outgassing, even with all this space weathering. But as you know, the jury is still out there on that. But I will talk about
one thing to keep in mind is the outer part of the solar system, the Oort cloud, is way outside the heliopoles of the solar wind. So it's exposed to the same interstellar environment as interstellar objects.
Right.
There is no difference between Oort cloud, comets,
and those have a tail. Right.
Well, what Amaya is saying is that the Oort cloud is exposed for a longer time, and then it's more affected by the cosmic ray. I mean, in this scenario.
So it's even more suppressed. But we do see comets from the Oort cloud.
As well, right. Yeah.
Okay.
In terms of, so have you applied the same analysis to
Borisov?
To Borisov? Because okay, perfect.
So the problem with Borisov is that it is a comet, and because it's a comet, it's very difficult to know the size, right? So because it's very dusty, and so the size from the HST images, Jewett et al. Had an estimate that it is between 0.2 and 0.5 kilometers in size, in radius. So if you assume that it has this size, and again, Borisov, you still have to, because we want to compare apples and apples, so we need to, I want to know if the cumulative number density of objects, of interstellar objects inferred from Borisov detection, if it agrees with what we are inferring from the detection of Oumuamua, do they both agree? So to estimate the cumulative number or the cumulative number density of interstellar objects that are similar or larger than Borisov, I'm basically just assuming that is 1 over the detection volume and that the detection radius is 3 astronomical units because that's when it was detected. And then what I'm going to do is assume this wide range of size distributions that I told you about, where I assume this broken power law and I assume a wide range of values for this Q1 and Q2. And I'm going to plug that in and I'm going to see where it lies in terms of the number density that the number density of objects larger than Oumuamua, because that's the number that I was comparing it to. And I get that it could be, I mean, this is the range that I get for Borisov in terms of the number density of objects larger than Oumuamua, and this compares with the 2 times 10 to the 15, so it is, you know, within the range, but again, there are a lot of uncertainties because, one, I don't know what is the size of this thing, because it is a comet, and it's difficult to measure the size. We were hoping that this thing will break up, and that one of the pieces will be like orbiting another piece, and that will be like a beautiful estimate of the size, but it didn't happen, unfortunately. But there is another issue, right? And is that in doing this, I'm assuming that they belong to the same population. But these two things are very different, right? Like one is not a comet, clearly, and the other one is clearly a comet, so they might not belong to the same population. So that's the issue there. And the last thing that I wanted to talk to you is, so we have these interstellar planetesimals. We don't know the number density yet, because Oumuamua has left more questions than answers in that regard. But we know that they are out there. We have calculated the estimates from the release of Oort cloud, exo-Oort cloud objects, from the release of planetesimal disks around other stars. And there is the possibility, so the idea is like, is there a possibility that these things are being trapped in star-forming environments? And could these interstellar objects act as seeds for planet formation? And the reason why we are interested in this is because, you know, there is this meter-sized barrier that is an unsolved problem in planetesimal formation, in planet formation, that challenges the growth of planetesimals that are sub-centimeter size to kilometer size, right? So because as the centimeter-sized particles grow, they become less coupled to the gas, but then they collide more energetically, and then they are less efficient at sticking to each other. They also fragment more frequently, and they can also bounce. So when they start growing, they start becoming, they have more, when they start, at the centimeter level, they start having more difficulties in growing larger, and also they have, they are still coupled to the gas, so they drift in due to gas drag, so they don't have time to grow before they drift in all the way to the stars. So, and this is what is called the meter-sized barrier. So the idea was, because this drifting time, it gets to the maximum when it's about a meter, things that are larger than a meter, they don't drift in that quickly. So if there is a way that you can pass that barrier, it will be much easier to form planetesimals, right, and to grow into kilometer-sized objects. So the idea is, like, if we could have interstellar planetesimals that are larger than a meter and that are trapped in these star-forming environments, and could they act as seeds, because they will be already large enough to be able to grow rapidly, accreting by the direct accretion of these sub-centimeter grains in the planetary disk. And also, as they settle into the, because their settling time into this mid-plane is fast, because it decreases as the particle grows, they can also get a boost in accretion as they settle down, right? Yeah, you had a question?
Just back on the point of Borisov, so that plot you showed that Borisov could be consistent with a wide range of size distributions. So